We have just seen in the first part of this video lecture what is the definition of law of large numbers. Law of large numbers is when we take a partial sum of a sequence of random variables, and the definition says if this partial sum minus its expectation, it converges to 0 when divided by the number of random variables. If it converges to 0, we say that the sequence of random variables, x1, x2, x3, and so on, they satisfy the law of large numbers. So there is a strong law of large numbers. That's when this convergence here is almost sure. There is the weak law of large numbers, which is when this convergence here is in probability. Then we saw Chebyshev's law of large numbers. We saw proof of Chebyshev's law of large numbers. Now we're going to see one which I find extremely beautiful and elegant, which is Cantalis' law of large numbers. This is already something from the 20th century, so rather recent mathematics. So Cantalis' law of large numbers, it now assumes the random variables are independent, so the conclusion will be stronger than Chebyshev's law of large numbers, but it requires further assumptions. They must be independent, not just pairwise covariances being 0. They must be independent, and also another stronger assumption, we assume now that their fourth moments are bounded. And however the conclusion is stronger, the conclusion, well, we will see in upcoming video lecture that it is stronger. It concludes that xn satisfies the strong law of large numbers, meaning Sn minus the expectation of Sn divided by n will converge to 0 almost surely as n tends to infinity. So let us now see the proof of a Cantalis law of large numbers. First, to simplify the argument, let us suppose that all the expectations of these random variables are 0. We can do that. Why can we do that? Because they all have finite fourth moments, and therefore they have finite second moments. We have proved that in two different ways, by using Jensen's inequality and by using Cauchy-Schwarz inequality. And that means they all have finite first moment, so we can subtract their expectation, and when we subtract the expectation of a random variable, we get one that satisfies this property, and that will preserve the assumption that the fourth moment is also bounded. Let us omit the proof of this fact and just assume their expectations are 0. We're going to expand the fourth power of the sum of n random variables like this. So we need some time here to understand this expansion. So what is this? This is x1 plus x2 plus up to xn to the fourth power. Okay, so we can do this like in primary school. We write the same term again, and we write the same again, and we write the same again. So what does it mean by the distributive property of products? What does it mean to consider Sn times Sn times Sn times Sn? Well, that means we're going to pick one of the terms here, and one of the terms here, and one of the terms here, and one of the terms here, multiply them. And we're going to do this for all possible different combinations and possibilities of how to choose terms from these expressions. And to be clear, what are these expressions? These expressions are four expressions which are identical: x1 plus x2 plus xn. So one way is to get x1 times x1 times x1 times x1. That will give us x1 to the fourth, which is what is here. We can get x2, 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 x2. That is x2 to the fourth power, and we can do that to each index I going from 1 to n, we can choose always the same term in each of these products. So here we have the sum over all possible indices I of the random variable I to the fourth power. Well, what else can we get? Well, we can get x1, x1, xn, xn, which means x1 squared, xn squared. Or we can get x3, x3, x2, x2. So that will be x3 squared, x2 squared, and so on. So it means we can choose two of these to be the same and the other two to be also the same but different from the first two. And moreover, we just like we can get x1, x1, x2, x2, we can also get x1, x2, x1, x2. So this number appears, this x1 times x1 squared times x2 squared. It appears a certain number of times. How many times? Well, exactly 4 choose 2. We can choose which ones will be those with a 1, x1 to be chosen, and the remaining will be the ones where we choose x2, and so on. So therefore, 4 choose 2 ways. Therefore, choose 2 ways to get 2 different indices, I and j, and both of them squared. Again, what we are doing here, we are expanding this product. What else can we get? Well, we can get continuing, what else can we get? Well, we can get xn, xn, x1, and x2, or any other arrangement where one of the indices appear twice and 2 different indices appear once each. Well, for that, we can choose all different ways, pairs of numbers j and k, and let's say j will be the smallest, and plus a third number I, which should be different from both j and k. And once we choose I, j, and k this way, in how many ways can we obtain this xi squared, xj, xk when expanding this product? Well, to be 4 factorial divided by 2 factorial, the 2 factorial is related to that we can choose I from 2 different places. And finally, the last term is when they're all different. So we can choose x1, x3, x5, and x8, for instance. They're all different, and then we're going to call I the smallest of them, j the second smallest, the k, and l the largest. And then for each possible choice of I, j, k, and l, which are all different and ordered like this, in how many ways can we produce those numbers? Well, we can permute all of these in 4 factorial different ways. And again, this 4 factorial will not be important for what will come now. Now we want to take the expectation of n as n to the 4. Why do we want the expectation? Because, well, we're going to use Chebyshev's inequality in the end, and Chebyshev's inequality requires computing expectations, or Markov's inequality, depending how we call it. So let us take expectation. Expectation of Sn to the 4th is the expectation of this sum, which is the expectation of this term plus the expectation of this plus, and that's exactly what is written down here. We got the expectation of Sn to the 4th. We get the expectation here inside the sum here, and also the expectation inside the sum here. And now what we notice from the last expression at the bottom is the following. All of them have some xk, and I did it deliberately, with a power 1. So this is xk to the power 1. And all the other indices are different from k. which means by independence, the expectation will factorize, and xk will be a common factor in these sums, the expectation of xk. It will be a common factor, and now let's not focus so much on the restriction of these indices, neither these numbers, because they will be all irrelevant in the end, because you're computing expectation of xk times expectation of other variables which are different from xk, which is written here. And I'm not bothering to write now the constraints of these sums either. All that matters is these variables, they are all different from k. This is why we can factorize one expectation here, one expectation here. And why do I not care so much by anything that is inside here? Because we're assuming expectation of xk equals 0. So this second line here is equal to 0. So we are left with these two terms, the sum of these n fourth moments of different random variables, and 6 times, 6 is this combinatorial factor that we have here, 6 times the cross moment, second moment of two different random variables from from the sequence xi and xj. So when we move forward, what we're trying to compute is this sum of n times the fourth moment, and we can bound this by n times m. And who is m? M being just the supremum of these fourth moments, which we assume to be finite. This is the assumption in Cantalis' law of large numbers. So this, we get this n times m, and now we have this factor of 6, combinatorial factor of 6, and we don't have n anymore, because now we had that sum I less than j of this expectation xi squared xj squared. So in how many ways can we choose I less than j and both between 1 and n? Well, this is exactly n choose 2. And by Cauchy-Schwarz inequality, we can bound this by the square root of the fourth moment of each of these variables, which is bounded by each one bounded by m, again by our assumption that fourth moments are all bounded. So we get again m here, capital M. So let's just expand. What is n choose 2? Will be n times 6. N choose 2 times 6 will be 3n squared minus 3n. Here we have to add back n, so we get minus 2n. So these two expressions here, they are equal. And this expression here is simply the assumption that fourth moments are bounded. The assumption that fourth moments are bounded, which together with Cauchy-Schwarz inequality give us that cross second moments are also bounded. This equality, I'm just expanding what does it mean n choose 2 and grouping the terms. And here we're just throwing away the 2n. So the expectation of, so the fourth moment of Sn, we managed to bound it by some term which has n squared in it. And this is the whole trick, this is the whole beauty that makes it work, the proof of Cantalis' law of large number work. Because now we're going to use Markov's inequality for the fourth moment. So this is a random variable, non-negative. We're looking at the probability that this random variable is larger than epsilon. We're going to take the fourth moment. So this will be the expectation bounded from above by the expectation of Sn over n to the fourth power divided by epsilon to the fourth power. And I'm just taking this n downstairs here. So this is what this n that appears here is just, this is a constant to the fourth power. I'm taking it out of the expectation. So this is what this n to the fourth that appear here. And now that we have expect the fourth moment of Sn at the numerator, we use the previous bound that we have just found. So we substitute and we get this expression here, 3m over epsilon squared n squared. Well, it is n to the fourth times this n to the squared here, they will cancel, and we get n squared downstairs. And now the key observation is this is summable. With this exponent, with this square in the denominator, this is summable. So we can use Borel-Cantelli lemma 1 to conclude that this will not happen infinitely often, or it will happen infinitely often with probability 0. And that means exactly that with probability 1, Sn over n will converge to 0. And this concludes the proof of Cantalis' strong law of large numbers. This concludes this video lecture.